turbomachinery, Pelton wheel. Today we will discuss about velocity triangle in Pelton wheel. So this is the Pelton wheel and this is the bucket. We imagine that we have a water jet from left to right like this. The water jet will hit bucket and immediately bucket will rotate counterclockwise to this direction and water will fall down vertically like this. One important thing that you should know when discussing about velocity triangle for Pelton wheel is the water jet here will hit one single point, then after the water jet hit the bucket here, the water immediately will fall down. So we assume that the velocity of tangential velocity here is equal in inlet and the outlet. So in velocity triangle for Pelton wheel, we only have one value of tangential velocity or u. Let's see in the inlet here. So the water jet flow from left to right, and we assume that it will flow tangent to the wheel to get the maximum rotation of wheel. So we draw the absolute velocity v1 horizontal like this. Then at inlet here, the bucket is almost parallel with the water jet to make sure that there are no losses occur. So we assume that component of relative velocity can be drawn parallel to the direction of water jet. And then this is the component velocity. This is the component velocity relative to the shape of blade, and another component velocity that exists together with VR1 here is the tangential velocity U1. So we draw the velocity triangle at inlet is like this. So we have V1 here, the absolute velocity. The V1 here is the actual velocity, and it also called a V-jet or velocity of jet. And we have U1, tangential velocity, and we have VR1 as the relative velocity at the inlet. Then, after the water jet hit the bucket here, we assume that the absolute velocity at outlet will flow like this. This is the V2 direction. So this is the absolute velocity at outlet. Then, because at the outlet here, the angle is 165 degree normally, so we draw relative velocity at outlet as like this. And then it continue with the tangential velocity U2 like this. And then for flow velocity or theoretical velocity, we assume that after the water jet hit the bucket here, the water will fall down vertically. So we draw, it is a vertical line here, and we mention as VF2. And then the component of VF2 is V wall velocity. So we draw V wall 2 here at this direction. The idea of drawing the velocity triangle at inlet and outlet is you must make sure that all the component velocity here will close loop the absolute velocity here, because we assume that V2 here is the original velocity or the real velocity of this Pelton wheel. So this is another simple hint or tips for you to remember how to draw the velocity triangle at the inlet. So normally in Francis turbine, we draw our velocity triangle like this. We have V1 here, and then we have U1 and VR1, then we have V1 and VF1. And then, because in Pelton wheel, we don't have any theoretical flow rate at inlet, so we don't have VF1 and VWL1. Now, our velocity triangle becomes like this. We have only V1 here, and U1 and VR1. And because the angle of the bucket at the inlet is parallel with the water jet here, the relative velocity need to be drawn parallel with V1. So we draw component velocity of VR1 parallel with V1, and U1 also need to be drawn parallel with U1. Then we shift a little bit the location of V1, because in real situation, the jet velocity V1 is flow horizontally. So we relocate the arrow here into this direction, then the VR is also stay at this location and this location. So this is the discussion about velocity triangle at inlet. So this is the velocity triangle at inlet. We have the absolute velocity V1 and we have its component U1 and VR1. So we could rewrite the value of VR1 here as V1 minus U1. And as I said previously, because the water jet here is hitting one single point before it flow as an outlet here, so we assume that the tangential velocity is remain constant. So we have U1 is equal to U2, and we assume it is equal to U. So we could rewrite our equation here becomes VR1 is equal to V1 minus U. So, and then another assumption for inlet here, because we don't have any VF1, velocity of flow here, we assume that VWL1 is equal to V1. And this is the calculation or assumption that we need to understand for the outlet. First, we need to understand that when V1 here hit the bucket, the velocity V1 here will flow according to the shape of bucket here, and then comes out as a VR2 here. And this is the this is V2, and this is the component of VR2. Because the velocity of jet here will flow on the surface of this blade, so we found that the energy losses on the bucket surface was occur. Then we could write an equation comparing the value of V1 comparing the value of VR1 and VR2 here as VR2 equal K times VR1, and K is the bucket friction of coefficient. From this equation, you could imagine that, for example, if the VR1 here is equal to 10 meter per second, because its flow on the surface of blade here, the output at the outlet here, the VR2 might be less than 10 meter per second. So it means that we need to multiply the value of VR1 here with certain coefficient to represent the value of VR2. So, and then from this velocity triangle, we could say that the angle here is theta, and the angle at this area is 180 minus theta. And this angle, we could calculate the cos of 880 degrees minus theta at this area is equal to U2 minus VWL2 divided by VR2. Then we could rearrange this equation become VWL2 equal U2 minus VR2 cos 180 minus theta, And then we could substitute the value of VR2 with this equation, and finally we could say V2 is equal to U minus K VR1 cos 180 minus theta.